Okay, how are you guys doing today?
Good.
Good. So I wanted to start off by announcing that we're going to have our midterm on November 1st. So that will be in a couple of weeks. We're going to do a review before the midterm, but just as a quick reminder, the basic structure of the midterm is going to be a hands-on exam. So we're going to give you 4 resistors in a bag, and you're going to have to identify the value of those resistors. So you're going to have to use a meter to measure the value of those resistors, and then you're going to have to convert that measurement and figure out what color codes would be on those resistors. Okay? And then we're going to ask you to construct a circuit with those resistors. The basic circuit is going to look like this. You're going to have a resistor there, one there, one there. You'll have your power supply over here, and you'll also have another resistor over there. So we'll ask you to build this circuit on a breadboard. We'll tell you what voltage to use, and then we'll ask you to measure the voltage and current for each of the resistors. And then you'll write down those values. So that is really going to be the whole midterm. Okay? So you guys have a few weeks to practice that. I strongly recommend that you do go and practice that. You can just grab 4 resistors out of the bins of resistors that we have on the side of the room. You can put the circuit together yourself, and I would strongly suggest that you have me or one of the other helpers check your work. So we're happy to do that. We're happy to answer any questions you have about that, about how to construct the circuit, about how to do the measurements, anything like that. But the sooner you can build it and try it out, the better off you're going to be. And really, it is a good idea to get one of us to check your work, because sometimes you think you know what you're doing and you put it together, but there is some slight misunderstanding in your knowledge, and if you don't have somebody else check that, you might never find out until the day of the test, when it'll be too late. So please build it ahead of time, try it out, and get somebody to check your work. And then the midterm itself will be on November 1st. We'll also do a day of review before the midterm. So our basic plan for the next few weeks is that today we're going to talk about the function generator and the oscilloscope. These are 2 pieces of equipment that are used in the lab all the time. We use them here because they're used out in industry quite a lot. So we'll talk about those today. We'll do an introduction to those. Next time we're going to start practicing basic soldering. So please remember to bring your safety glasses next time. Okay? It's especially important to have those when you're soldering, because the solder can splatter and it can get in your eyes if you're not careful. So please bring your safety glasses next time for the basic soldering. That'll give you a chance to practice your soldering. The class after that, we're actually going to start working on our fiber optic communicator kits. So that'll be next Monday. So please, everybody, bring your fiber optic communicator kit next Monday. So we'll start working on those. We'll do probably the transmitter on Monday. We'll do the receiver on Wednesday of next week. And then the week after that, Monday we'll do the review for the midterm, and then Wednesday will be the midterm itself. Okay? So that's how the next few weeks are going to go. So any questions about that? Okay. We'll use our knowledge of the function generator and oscilloscope when we are testing out our fiber optic communicator. Okay? So today we're going to learn about those instruments, and we'll use them to actually test out our transmitter and receiver. So that's why we have to know about it ahead of time. Okay. So that's a little bit about the midterm. Today, we're going to start with a review of Kirchhoff's voltage law and Kirchhoff's current law. Okay? So we'll talk a little bit about that. We'll talk about voltage dividers, and then we'll go into our lecture. So we'll start talking about the function generator. We'll talk about what it is, how we use it, and why it's important. Then we'll discuss the same things about the oscilloscope. We'll do a quick preview of today's lab. For the lab today, you guys are going to hook the function generator, which creates signals, straight into the oscilloscope, which measures signals. So you'll use the oscilloscope to visualize the signals that are coming out of the function generator. Okay? So we'll talk a little bit about that in the lab. Any questions before we get started?
Is that a midterm? Is that going to be open to us? Are we going to have access to the color code chart?
So for the midterm, you'll be allowed to bring in 1 page of notes, 8.5 by 11 front and back. So you are certainly welcome to write down the color codes on that piece of paper. I would recommend that, because that will definitely be part of the midterm. And you can write down anything else that you want on that sheet of notes. You'll also be allowed to use a calculator. You will not be allowed to use any cell phones or the internet. Okay? So you won't be able to use cell phones even for a calculator. So this is why it's important to have your own calculator that you bring in with you, because you'll need to use a separate standalone calculator on the midterm. Okay? And it's much better to get familiar with it ahead of time rather than trying to figure it out on the day of the test. Okay? So, yeah, other questions? Okay, cool. So then, let's start with a quick review of Kirchhoff's voltage law and Kirchhoff's current law. So, I know it's been a while now, but does anybody remember what Kirchhoff's voltage law says? It has been a while. All right. So the basic idea with Kirchhoff's voltage law was that if you look at any circuit, you can draw loops around that circuit, right? So a loop was any path that started and ended in the same place in a circuit. And we said that Kirchhoff's voltage law states if you add up the voltages around any loop, they add up to 0, right? So suppose that we had a 12-volt supply here with the positive side being up here and the negative side being down there. And then we had these resistors, and maybe we had 5 volts across this resistor, and then 3 volts there, and 4 volts down there. What we would see is that we could draw a loop around this circuit, and we could start anywhere that we wanted. So we could start here, for instance. And each one of these resistors would have a polarity to the voltage, right? So for instance, the left side of this top resistor would be more positive than the right side. The top of this resistor would be more positive than the bottom. So if we go in a loop around this circuit, we could start up here and go down here. We would be going down by 3 volts. So if we start at 0, we would be at -3 here. And we go down by another 4, so we'd be at -7 over here. Then we'd go up by 12, so we'd be at 5. Then we go down by 5, and we're back to 0. So we add up all of those voltages, and they add up to 0 volts. Okay? Questions about that? So a loop can start and end in any place or can start in any place and ends up in the same place. It can go in any direction. So this would be one loop around the circuit. We could have picked another loop just over here on the right-hand side. Bless you. So what happens is that these two resistors are in parallel, so they have the same voltage across them, right? So if we had picked a loop on the right-hand side, we could have started here, maybe, and gone up this way. We'd go up by 3 volts, and then we'd go down by 3 volts. So we end up back at 0. So if we add up all the voltages around that loop, we get 0. And we could do the same thing around the outer perimeter of this circuit. And if we added up all of those voltages, we'd get 0 as well. So a loop can start anywhere you want. It can go any direction you want. And as long as it ends up back in the same place, all of the voltages add up to 0. Okay. So that was Kirchhoff's voltage law, or KVL for short. Okay. Kirchhoff's current law talks about currents. Does anybody remember what Kirchhoff's current law says? Okay. What's that?
What goes in must come out.
Yeah, exactly. So if you look at a junction on a circuit and you add up all of the currents that are going in, they have to have the same value as all of the currents going out. So if we know that we have 100 millivolts going, or milliamps going in there, and we have 80 milliamps coming out there, how much do we have in this? 20. Exactly. And are they flowing in or out? Out, exactly. So we know that we have to have a total, well, we have a total of 100 going in, so we have to have a total of 100 going out. Okay? And you can do this with any number of wires. So if you had a junction that had, 5 wires coming into it, then you added up all of the currents going in, they would add up to the same number as all of the currents going out. So that would be fine. You can even do it with a junction of just 2 wires, right? You've got 50 milliamps going in, say, then you know that you would have 50 milliamps going out as well. It's not very interesting, you don't learn very much, but it still holds true. So a junction is any point on the circuit, and if you add up all of the currents flowing into that junction, they will add up to the same number as all of the currents flowing out from that junction. So that's Kirchhoff's current law. So that's what these two laws said. The reason that we care about them is because they help us to understand circuits and design circuits. If you are looking at a circuit and you remember these two laws, often they can help you to analyze that circuit and understand how the current is moving around through it, how the voltage is distributed throughout the circuit, right? If you knew that there were 3 resistors in a loop and you knew the voltages on 2 of them, then you could figure out the voltage on the 3rd one, right? If you knew the currents flowing into a junction from 2 wires and there was only 1 left, you could figure out the remaining current that way using Kirchhoff's current law. So these are very useful for helping us to understand and analyze circuits and to design our own. Okay. So then let's briefly mention voltage dividers as well. A voltage divider was a fancy name for two or more resistors in series, right? So say we had 36 volts over here, and each one of these resistors was 500 ohms. Okay? We could simplify this circuit and say that this was equivalent to a circuit with just one resistor. And how much resistance would that single resistor have?
Okay.
Yeah, 1 kilo. These are in series, so they simplify by adding together. So this becomes 1,000 ohms. Okay? And then we could use Ohm's law to figure out how much current is flowing through that resistor, right? We've got 36 volts and 1,000 ohms. So how much current would be flowing through that resistor? So Ohm's law is like this, V, I, R. So we say I equals V over R. So that is 36 over 1,000.
36 milliamps?
Yeah, it's 0.036 amps. So that's 36 milliamps. Sort of a shortcut way to see that is that if you've got 1,000 ohms, then the current is always equal to the voltage in milliamps. So we had 1,000 ohms, 36 volts, then we have 36 milliamps. Right? If we had 20 volts, it would be 20 milliamps, and so on. So we have 36 milliamps flowing through this circuit. We have a total of 36 volts. We have 36 milliamps flowing through here. We could find the voltage on each of these resistors, right? V equals I times R. So this is 0.036 times 0.036 amps times 500 ohms. Comes out to be 18 volts on each of these resistors, right? So the punchline is that each of the resistors has half of the total resistance. Each one gets 18 volts, or half of the total voltage. Okay? So that's how voltage dividers work. If the top one had a quarter of the total resistance, then it would get a quarter of the total voltage. If the top one had a tenth of the total resistance, it would get a tenth of the total voltage. So by putting these two resistors in series, they divide the voltage among themselves. So that's why you have a voltage. That's why you call it a voltage divider. Okay? There's a formula that we can use for voltage dividers if the numbers don't come out quite so cleanly, right? So maybe it's not. So the formula is VR1 equals V total times R1 over R1 plus R2. So in this case, that would be the total voltage is 36 volts times, bless you, 500 over 1,000. So that's 36 times 1/2, or 18 volts. So you could use this formula to find the voltage on a particular resistor as well. Yeah?
What's the name of the formula? The particular law or name?
You could call it the voltage divider formula. Yeah, there's not a real special name for it. So any questions about voltage dividers? Okay, cool.
Question.
Yeah.
So for that formula, if you have
Yeah.
4 resistors, it would just be R1 plus R2 plus R3.
Yes, exactly, exactly. Okay, cool. So that's what I wanted to say for our review. So let's go on and talk about some new stuff. So the first thing I want to talk about is function generators. Okay? So a function generator does just what it sounds like. It creates a voltage signal. So it creates a voltage that changes over time. So you might say, why would we want something like that? Well, we generally use function generators for testing other circuits or other equipment, okay? They can be used as a stand-in or a replacement for certain things. So let me give you an example. Before I came here, I was working at Lawrence Livermore National Lab, and when I was there, I was working on a project to test a very large laser system, which was fixing giant lenses, okay, giant optical lenses that were probably 24 inches on a side or so. And the way that the system worked was that this laser would shoot tiny pulses of energy at the lens, and it would carve out small holes in the lens. I was asked to create a system that would measure and count the number of pulses of laser energy that were shot into one of these giant lenses. So, sort of the first thing that you might think about would be to go down next to this giant machine and write a program sitting right next to it and measuring so that I could actually have the machine right there and run it every time that I wanted to test my program to see if my program was working right. So that's sort of the first idea, but there were some problems with that. First of all, the machine was running all the time. It was in use already, so if I was sitting there next to it and using it to test my program, that would be taking away from time that it could be doing real work. So that was sort of a downside. Also, it was in a clean room environment, so I would have to get suited up in one of those bunny suits from head to toe every time I wanted to use it out. So that was a hassle. So I wanted to be able to write this program and test it out without having to use the actual machine to do the testing. So what I was able to do is that I was able to use a function generator to take the place of this giant machine. Basically, the thing that I was measuring was a voltage pulse for every time that the laser fired. So instead of reading those voltage pulses directly from the machine, I set up a function generator to create those pulses and then I hooked that up to my my computer to test out my program. So that was much easier. The function generator could sit on my desk right next to my computer. I could use it as much as I wanted. It was not taking away from anybody else's time, and I didn't have to get all dressed up in order to test it out. So that's the type of application where function generators are typically used. They're used to simulate some other machine or some other signal that might be difficult to get. Okay? Yeah.
So, why use a power supply instead of a function generator? When you're
Oh,
testing?
why not use a power supply?
No, I mean, like, why use a function generator instead of a power supply? What's the difference?
Oh, yeah. So a power supply creates a fixed voltage. So that's good for supplying energy when it takes the place of like a battery or something like that. A function generator creates voltages that change over time. So you can, I'll tell you about it in a minute, but you can use it to create lots of different types of signals. So actually, yeah, let's talk about that. So basically, we can use the function generator to control three different things about a signal. The first thing that we control is the shape. The shape of the signal. So there are many different shapes that a signal can take on. The basic shapes that our function generators create are square waves. They look kind of like this. Triangle waves that look sort of like this. And sine waves that look like this. So we can use the controls on the function generator to specify which type of wave we want to create. Okay? So the power supply creates a constant voltage that usually has and is usually able to supply quite a bit of current, right? These can supply maybe 3 or 5 amps.
Oh, wow.
Yeah. The function generator allows us to create these different shapes of signals, but usually has a very small amount of power.
Okay.
So they're not usually used to power something. Okay, so like I said, there's 3 things that we can specify about the signal. We can specify the shape, we can specify the amplitude, the amplitude is how big the signal is. So a large amplitude signal would be something like this. That would be a large amplitude sine wave. A small amplitude would be something like this, right? So the amplitude is how big it is, how much voltage we're giving. Right? A large amplitude has a lot of voltage. A small amplitude signal has a smaller amount of voltage. And there's different ways that we can specify the voltage or record it. If we look at the difference between the top or the peak of the highest point on our signal and the lowest point on our signal, then we call that difference the peak to peak voltage, because it's between the top peak and the bottom peak of our signal. So that would be the peak to peak voltage. There are other types of voltages that we can specify as well, but I don't want to go into those just right now. So anyway, we talked about choosing the shape of our wave, choosing the amplitude, and then the last thing that we want to specify is the frequency. The frequency is how many times per second a signal repeats. So, for instance, that might be kind of a high frequency. And if you had something like that, that would be a low frequency. Notice the amplitude, I tried to draw the amplitude about the same. But the frequency changes. So this one repeats a lot of times in 1 second. This one repeats fewer times in 1 second. So these are the three things that we specify when we're creating a signal. We specify the shape, the amplitude, and the frequency of that signal. Talking about frequency, another thing which is related to frequency is the period. The period is the amount of time between a spot on a signal and the same spot on the next signal. So another way to say that is it's how long it takes for one cycle of the wave to complete. And period and frequency are related to each other. So the longer it takes for a signal to complete, the lower the frequency is, the fewer times it happens in 1 second. So we say that frequency is 1 divided by the period, and the period is 1 divided by the frequency. So if you know the period, you can calculate the frequency, and vice versa. Okay. So, function generators. The fundamental thing about function generators is that they create the signal. So if you need to have a signal, you can use a function generator to create it. If you're working with the signal and you want to change that signal, you have to go to the function generator to change it, right? And we'll talk about the controls, bless you, in a minute, and see how you can choose and specify each one of these things. But you would use the controls on the function generator to change that signal. Okay? Any questions about function generators? All right. So let's actually see the controls on the function generator and see how we can specify each one of these things. So this is our function generator. Hang on here. Okay. So the first thing that we want to choose is the shape of the signal. And we use these buttons down here to specify the shape. So if we push this button on the left, the light lights up over that button. And we know that we're creating that type of signal. Anybody guess what kind of signal that is? Square wave, yeah, exactly. What about this one there? Triangle, perfect. And then this one over here is a sine wave. Exactly. So we use those buttons to choose which type of wave we're creating. The next thing that we can specify is the amplitude, and we use this knob down here, this AMPL knob. AMPL stands for amplitude. If we turn this clockwise, that makes the signal bigger amplitude. If we turn it counterclockwise, that creates a smaller amplitude. The last thing we want to specify is the frequency. And we do that. There are actually two controls that work in conjunction to specify the frequency. The first set of controls is along the top here. These are the frequency range buttons. So this specifies what frequency range we're in. So right now, we're over here, we're in the 1K or 1 kilohertz range. A hertz is 1 cycle per second. So 1 kilohertz means 1,000 cycles per second. So that means that our function is going to be happening around 1,000 times per second. But this doesn't specify the frequency fully. This just specifies the range. In order to get the actual frequency, we have to multiply this number by the number on this dial over here. So, for instance, right now, we're in the 1 kilohertz range, but the knob is pointing to the 0.9. So to get the actual frequency, we would multiply this 1,000 times 0.9, and that would give us 900 hertz. So right now, this is creating a 900 hertz signal. Yeah?
How do you choose the voltage?
So, right, that's a good question, because we can turn this knob back and forth, but it doesn't tell us exactly how much voltage it's creating, right? So the answer is that we actually have to use a separate piece of equipment to measure the voltage. And that's what we can use the oscilloscope to do that. And we'll talk about that in just a second. So remember, the function generator creates the signal. We can specify the shape, the amplitude, and the frequency of the signal. And anything that we want to change about the signal, we have to change it using the function generator. Any questions about that? Yeah?
Are there certain waves to be used for certain things, or not?
It just depends on your application. Like, for instance, for the application that I talked about earlier with the laser, I know that the signals coming out of that laser are square wave pulses. So I would set up my function generator to create square waves. When we are using our fiber optic communicator kits, the waves that get sent between the transmitter and the receiver are mostly sine waves. Sound is made up of lots of different sine waves. So we would create a sine wave in that case. So it just depends on what you're trying to mimic, really.
But if you use like a different one to the one that you're supposed to use, does it affect anything?
Well, yeah. I mean, so it would make a difference. It just depends on what type of application you're talking about. So if you were looking for square waves and you were creating sine waves, then the detector that you made might not function correctly or something like that. So it's important to create the correct type of wave for your application. Yeah. Other questions? Okay. Okay, so let's talk about oscilloscopes for a minute. Oscilloscopes are sort of like cameras for electrical signals. They allow you to look at electrical signals over a short period of time. It's almost like a movie camera for an electrical signal. You might ask why we need a new instrument to measure electrical signals, right? We've already got multimeters to measure signals. They can measure voltages, right? They can measure current, they can measure resistance. Why would we need a different piece of equipment? And the answer is that multimeters only measure your signal at one particular instant. And oscilloscopes let you see a picture of your signal over a period of time. Also, the multimeters will give you an average of your signal if you're looking at a DC voltage. So, for instance, if you were looking at these sine waves, maybe all of these waves have an average of 0 volts. All the sine waves, all the square waves, all of the triangle waves have an average of 0 volts. So just looking at the average voltage, you wouldn't be able to tell what shape the wave was, what amplitude it was, what frequency it was. You would only be able to see the average and see that the average was all 0. So all of these waves would look the same if you were measuring them with a DC voltmeter. But you can tell by looking at them over time that they're actually different shapes, different amplitudes, and different frequencies. So the multimeter allows us to measure the wave over time. Okay? So it acts kind of like a video camera for electrical signals. And just like a video camera, it allows us to zoom in and zoom out on our signals. Okay? So if you are looking, if you wanted to take a video of a place and get to know it a little bit, you probably want to start out with a wide shot, right? That shows you sort of a wide landscape view, and you could get a sense of what's going on in general. And then maybe you would want to see some more detailed shots of little features, right? So maybe if you were doing a video about architecture, you could start with a big shot of the entire building to see what was going on, and then you could go with more zoomed in shots of the doors and the windows and the columns and the trim. Well, the oscilloscope lets you do the same sort of thing. It lets you to zoom out and see the whole signal, and then it lets you zoom in on particular parts that are most interesting to you. And its zoom is actually a little bit fancier than the zoom that you get on a camera. With the camera, you just have one control, zoom in or zoom out, right? With the oscilloscope, you can actually zoom in and zoom out on the horizontal direction, and also zoom in and zoom out on the vertical direction. So you have two separate zoom controls there, okay? So the oscilloscope lets you look at signals. It's like a camera, it lets you see them, it lets you zoom in and zoom out, but it does not change the signal itself, okay? Remember, the function generator creates the signal, so if you want to change the signal itself, you have to change it using the function generator. The oscilloscope only lets you see the signal. Just like taking a picture of the building is not going to change the building, the oscilloscope is not going to change the signal that you're looking at. It just lets you look at it in different ways. Okay? So, enough of this talking about it. Let's actually pick this up and look at some real signals. Okay? So, in order to work with these two devices, we need to use cables to hook into them. This is the cable that you use for the function generator. Okay? You can get these cables from the back of the lab room there. They're hanging up right beside the electronics tool room window. You just grab one. Okay, it's got a little silver end on it. So this is the function generator cable. Okay. The other end has these two little alligator clips on them. One is a red lead, the other one's a black lead. The silver connector on this cable is called a BNC connector. So the way that it works is you push it in, and then you give it a little bit of a twist, and then it makes a secure connection. To hook this up to the function generator, you're going to attach it to the little BNC port on the far right-hand side. Okay, so you push it in, you give it a little turn, and it makes a secure connection. This is labeled output. Okay. There are these other two BNC connectors on the front of the function generator as well. Do not hook up to these. These are used for other things. So you hook up to the one on the far right. Okay. To connect to the oscilloscope, you're going to use this type of cable. This cable is fancier and more expensive, so we ask that you check these out from the electronics tool room window at the back of the lab. Okay, so you'll just fill out a little card that has your name on it, and then give that to them, and they'll give you one of these cables, and then when you return the cable, they'll give you your card back at the end of the lab. Okay, so this is the oscilloscope cable. The end of the oscilloscope probe has two connectors on it. The one that is hanging off the side that has the little alligator clip is ground. So you're going to hook this one up to ground. The one that has the little pointy end on it is the probe. The way that the probe works is that it's got a little shield around it. You pull the shield back and it exposes a little hook. And then you can use that hook to grab onto whatever signal you want to measure. Okay? So the little alligator clip is ground. The little shielded tip is the probe. So when you hook this up to the oscilloscope, you're going to hook the non-probe end onto one of these cables or connectors on the front. These are also BNC connectors, okay? So it is possible to connect to use the BNC, or let me say this again. You could screw the oscilloscope cable onto the function generator and put the function generator cable onto the oscilloscope. The probes would allow you to do that, but it would screw up your signal, okay? So don't do that. Please make sure that you use the oscilloscope probe on the oscilloscope and the function generator cable on the function generator, okay? All right. So now we've got our cables hooked into our two devices. Ordinarily, you would have a circuit that you were analyzing, right? So you would hook the function generator up to part of the circuit, and then that would inject a signal into your circuit. Your circuit would do some manipulation on that signal, it would process it in some way, and then you could measure the output of your circuit with your oscilloscope. Okay? That's normally how this would work. But today, we're really just interested in learning about these two pieces of equipment. So today, we're going to hook the function generator straight into the oscilloscope. And we're just going to measure the signals that are coming out of the function generator with the oscilloscope. Yeah?
Well, if you're going to hook the function generator up to a circuit, how would you know what to set it at before you hook it up to the oscilloscope?
Right, so that's a good question. Because we don't have the voltage measurement on the function generator. Oftentimes, you will do more than one measurement with the oscilloscope. So you'll notice that the oscilloscope actually has these 4 separate ports on the front. So you can actually measure 4 different signals at the same time with this oscilloscope. So often you would measure the input with one of these ports and then the output with another port. Yeah, different oscilloscopes work in different ways. Some of them only have 1 port, some of them have up to 8 ports. I think the ones you guys have 2 ports. But yeah, that's often what you do. You measure the input and the output. So we are going to hook the oscilloscope straight to the function generator just to measure what's coming out. So we're going to hook the black lead from the function generator. This black lead from the function generator, this little alligator clip, to the black alligator clip from the oscilloscope. Okay? These are the 2 ground leads. You have to hook those 2 together. Then we're going to hook the red lead from the function generator to the probe of the oscilloscope. Okay? So you're going to make those 2 connections, ground to ground, and then signal to probe. And once you do that, you should be able to see a signal up here on our oscilloscope. Okay. So we're creating a signal with our function generator and we're measuring it with our oscilloscope. But what we see is that part of the signal looks like it's off the top of the screen, and part of it looks like it's off the bottom of the screen. So in order to get a better picture of what's going on, we actually want to zoom out with our oscilloscope so that we can see the signal more fully. The way that we're going to do that, we're going to zoom out in the vertical direction, and to do that we're going to use this knob on the oscilloscope. If we turn this counterclockwise, we can zoom out. Now we can see the tops and the bottoms of our signal. If we turn this knob more, we keep zooming out, and the signal keeps getting smaller and smaller on the screen. Remember, the signal is not actually changing. It's only the way that we're looking at the signal, right? Okay. So we're like pulling back and seeing it from farther away, or zooming out, but the signal itself is staying the same. So we can zoom back in. The other thing that we could do is we could zoom in the horizontal direction. So right now this looks pretty good as far as horizontal zoom, but we could still change it if we wanted to. So we use this knob on the far right-hand side to change the zoom. If we turn it counterclockwise, we're zooming out, so we see more of the signal. Turn it clockwise, we're zooming in, so we're seeing the signal closer and closer. Okay? So again, we're not changing the signal itself, we're only changing the way that we look at it. Any questions about that so far? Okay. So the oscilloscope has some features that help us to sort of measure our signal and get more information about it. Okay? So let's talk about those for a minute. All right. Okay, so some of the more obvious, or the clearer features are these horizontal and vertical lines on the screen. These break up the screen into these little boxes called divisions. Okay? And the divisions help us to measure our signal. So right down here it says CH1 for channel 1, 2.0 volts. That means that each of these boxes represents 2 volts. It's 2 volts tall, okay? So if we look at our signal and count how many boxes it is from the top to the bottom, we can estimate how many volts it is from the top to the bottom. So imagine that the signal went all the way up to the top of this box and all the way to the bottom of this box. Then we'd have 1 box, 2 boxes, 3 boxes, 4 boxes from the top of our signal to the bottom. And each box represents 2 volts. So how many volts would it be from the top of the signal to the bottom? 8. Exactly. So we can see that it doesn't go quite to the top or quite to the bottom. So it's a little bit less than 8 volts, maybe 7 volts or so. Okay? So we can use that to measure the amplitude of the signal. We can also see how much time there is per division. This says 100 microseconds per division. That means that each one of these boxes is 100 microseconds long. So that's 100 microseconds, that's 100, or another way to say 100 microseconds is 0.1 milliseconds, right? So 10 boxes would represent 1 millisecond. So if our signal was 10 boxes from the start to the end, that would mean that it had a period of 1 millisecond, right? If it had a period of 1 millisecond, what would the frequency be? Remember, frequency is 1 over the period, right? Well, it would be, remember, okay, so 1 millisecond is 0.001 seconds, right? Yeah. So the frequency would come out to be 1,000 hertz. Okay? 1 over 0.001 is 1,000 hertz. So a period of 1 millisecond gives a frequency of 1,000 hertz. We can see there are 1, 2, 3, 4, 5 boxes every half of the screen, so there's 10 boxes on the screen. The signal doesn't quite complete in one screen. So the period is a little bit longer than 1 millisecond, so the frequency is a little bit lower than 1,000 hertz. So it's about 900 hertz, like we said when we set it up, right? So we can use the screen and count the number of boxes on the screen to figure out the voltage and the frequency of the signal. There are also several other things about this signal that are shown on the screen. First of all, there's this little 1 over here with an arrow. That indicates the 0 level. So that means that 0 volts is right here. Currently it's right in the middle of the screen, but it does not have to be. We can use this knob on the oscilloscope. Make that a little brighter. We can use this knob to move the signal up and down. So if I turn the knob one way, the signal goes up on the screen. And you'll notice that as that happens, the 0 level indicator goes up as well. So it's telling us that 0 is still in the middle of this sine wave, even though we've moved the sine wave up on the screen. Okay? So you can move the signal up and down, but that 0 level still shows you where 0 is. In this case, it's in the middle of the signal, but that's not true for all signals, right? Some signals, 0 might be down here at the bottom, and the signal is all positive. Or 0 could be up at the top of our signal, and we could just have a negative signal. So it's important to show where 0 is so that we know we know that when we're looking at the screen. Okay? The other thing to notice is this arrow on the right-hand side. That's called the trigger level. This tells our camera when to take the picture. Okay? Basically, what's going on is that this wave is repeating, 900 times a second. So this camera takes these pictures of the wave, and we want it to take the picture sort of in the same place every time, so that the waves lie right on top of each other. And this trigger level tells it how to do that. The important thing is that the trigger level is between the top and the bottom of our signal, between the top and the bottom. If it's somewhere between the top and the bottom, then our wave will come out nice and fixed, and it will be easy to look at it and measure it on the screen. We can set the trigger level with this knob up here. This is in the trigger portion of the oscilloscope controls, and it's this, the knob is labeled level. I know you can't see that right now, but it's got a level label next to it. So if you turn it one way, you'll notice that that arrow moves up. If you turn it the other way, the arrow goes down. And you see, as long as it's between the top and the bottom of the signal is fixed and clear on the screen. If I move it too far and it goes off the bottom, yeah, the signal starts moving around like this. Okay, and then you can see it would be very difficult to estimate the voltage or the time or the frequency of this signal, because it's changing all the time. So if you see a signal looking like this on your screen, it usually means that your trigger is in the wrong place. So you have to move the trigger level up so that it's between the top and the bottom of your signal. Okay? So any questions about that? Okay. Cool. So say that I wanted to set this signal so that it was 8 volts peak to peak. How many boxes would that be? 4, exactly. So what I can do is I can move this so that the 0 level is sort of right in the middle of the screen, and then I can go to my function generator, and I'm going to turn the amplitude knob on the function generator. And when I do that, you should see the signal getting a little bigger on the screen. So yeah, so you can dial it in there until it's about 4 boxes from the top to the bottom of the signal. Okay. But now we said that we could zoom in. Yeah, sorry.
Is there something on that that tells you exactly what the voltage is, or do you just have to kind of like look at the squares and guess?
There is something on here. There's a measurement function on the oscilloscope screen. The reason that I start with the squares is because I think it's important to have sort of an intuitive understanding of how that works, so that you can just kind of glance at a screen and estimate yourself about how big a signal is or about how fast it's moving. The oscilloscope has measurements that are built in that you can use that will give you a precise reading, but sometimes they can be fooled. Like if there's noise on the signal or things like that, they can be thrown off. So it's important to be able to just look at it and estimate it. But yeah, let's talk about the measurements for a minute. So on the top of the oscilloscope, there's this button that says measure. Okay? So if you push the measure button, this brings up a number of menus on the right-hand side of the screen. Okay, so on the right-hand side here, you can see that we have these measurements. So right now, it's showing the channel 1 maximum value. There's also channel 1 frequency, channel 2 peak to peak, and so on. So all of these are measurements that can be made on your signal. So in order to change these around, what you can do is you can push the button which is next to the measurement. Okay? So your oscilloscopes work a little bit differently. In the lab, there's a little knob on your oscilloscopes, and you can use that to change the measurement. But in this case, you push the button. The first thing that it says is source up there. Source right now is channel 1, so it's making a measurement on channel 1. If you had a signal connected to channel 2 or channel 3, you could measure signals on those channels as well. Right now we're just measuring channel 1 though. The type is max right now, so this is giving you the maximum value for your signal, and it's saying that the max value is 4.08 volts right now. So that's saying that the maximum up here is about 4.08 volts. And that's pretty close to what we wanted, right? We wanted 8 volts from the top of the signal to the bottom. So that would be 4 volts from the middle to the top, right? So that's pretty close. We could choose a different type of measurement though. If we push this type button, this allows us to scroll through the various types. So each time you push the button, it picks a different type. So right now, it's showing the cursor RMS value. There's rise time, fall time. There's all these different measurements that we can make about our signal. Don't worry if you don't understand all of these words right now. We haven't really talked about them. Okay. Frequency is an important one. Right now, the value has a question mark on it. So it's saying that it's not able to measure the frequency right now. And the reason is that we don't have a complete cycle of the signal on our screen. And the oscilloscope can only measure what it sees on the screen. Okay? So it needs at least one complete cycle in order to measure the frequency. So what we would have to do is we would have to zoom out so that we can see at least one complete cycle, and then it should be able to give us a frequency measurement. So let's zoom out in the horizontal direction here. So now we're getting more than one cycle on the screen, and so it's telling us that we're at about 975 hertz. Okay? So we could adjust, say we wanted to have 1,000 hertz in our signal, we could adjust that on our function generator. We can go back over here and turn the frequency knob on the function generator, and now it's just over 1,000 hertz. So you can play around with it until it gets as close as you want, and then call it good. Okay, so we can measure the frequency there. We can make other types of measurements. We can measure the period. Remember, the period is 1 over the frequency, and we said that for 1,000 hertz, we should have about 1 millisecond period. So that's confirming what we figured out before. The mean. So this is something. So we said that we wanted to have a peak-to-peak voltage of about 8 volts. And we looked on our screen, and we figured that this was about 8 volts. But now it's telling us that the mean value is 500 millivolts. It's pretty close to 0 volts. So why would that be? Why would you have a 0 volt signal when we were talking about an 8 volt signal a minute ago? Well, what is the mean? What's another name for the mean?
Average.
Average, exactly. So this is telling us that the average of the signal is about 0. So that's saying that the signal is above 0 about half the time and below 0 about half the time. And since that's the case, since it's about half above and half below, it comes out that the average is pretty close to 0. Okay? And this is what you would see if you measured the DC voltage on a multimeter. You would see an average of about 0 volts on this one or on any of those other shaped waves. So the oscilloscope can measure the average value as well. So here we finally get to the peak-to-peak value, which is what we really wanted to measure before. So this is saying that the peak-to-peak value is about 7.8, 7.9 volts. So that's a more precise value. We eyeballed it and said it was pretty close to 8, but this is telling us it's about 7.9, so we could adjust the amplitude a little bit and make that a little bit bigger and really dial it in, get as close as possible to 8 volts. Okay? The other thing about the oscilloscope is that it gives you more accurate measurements when the signal is as large as possible on the screen without going over the top or the bottom, without going off the top or the bottom. So you want to zoom in as much as possible without having the signal go off the top or bottom. So if we get up that high, that gives us the most accurate signal measurement possible. Okay. So we can adjust it there. So that'll give us the most precise measurement. If we were to zoom out, we would see that this measurement degrades. And so like when it's down there, it's telling us that it's 8.8 volts. But that's really not a very accurate measurement. It's like trying to read a ruler from across the room, right? It looks really small. You can't really see what's going on, so you make your best guess. To get a more accurate measurement, you want to be real up close and personal with it. So you want to zoom in as much as possible on the oscilloscope to give it the best possible chance. Okay? Okay, so that's a little bit about measurements. Once you have picked the measurement that you want, you can hit the back button down here, and then that measurement is displayed up here on your screen. So now it's showing the peak-to-peak measurement for your signal right there. So you could do the same thing and choose a different measurement for each one of these spaces on the side of your oscilloscope. On your scopes in the lab over there, the measurements get displayed on the bottom part of your screen down here. Okay? So you can do the same thing. You can choose which measurements you want, but they show up down at the bottom rather than on the side. Okay? All right. So that's a little bit about the oscilloscope. So let's do a quick preview of today's lab. So the first thing that you're going to do in the lab today is that you are going to you're gonna get cables for your oscilloscope and your function generator, and you're gonna hook them together. And then you're going to create specific types of waves on your function generator, and you're going to look at them with your oscilloscope. So the first type of wave that you're going to create is a triangle wave. You're going to make this wave at 1,000 hertz and 4 volts peak to peak. PK-BK is the abbreviation for peak to peak. Now it says measure and sketch the triangle wave on your graph. Okay? So when you do this, you should try to be as accurate as possible. Your graph has the little divisions drawn in for you. They're the same number as of divisions in the graph as there are on the oscilloscope screen. So if it is 5 divisions from the top of your wave to the bottom of your wave on the screen, you want to make sure you draw it like that in your book. Okay? There is a place to write in the number of volts per division and the seconds per division in your book. So you should write those in as well. The idea is that if you were to come back to this in 10 years and look at this signal, you should be able to understand how big the signal was, understand what frequency it was at, and understand what shape it was just by looking at this graph. Okay? So there are a number of things called out here that you should include. So it says include the voltage and time settings. That's the volts per division and the seconds per division. It says include the zero level and the trigger arrows. So that'll, remember, the zero level is the indication over here that shows you where 0 is, and the trigger level is the arrow on the right-hand side that specifies where the trigger is taking place. And then below that, it says indicate and measure the peak-to-peak range on the sketch. So when you're drawing this, you would do something like this. You've got your box on your graph there. Your box has all of the divisions drawn in. So you would sketch your signal. So this would be a triangle wave. So you would draw it out. You would make sure that you have the correct number of divisions from the top of your wave to the bottom, and also the correct number from one peak to another. So if it's 4 divisions from one peak to another on your screen, you want to make sure that you draw it 4 divisions on your graph. Okay? So you would draw that in. You would make indications for the 0 level and the trigger level. So you would do something like this. You would draw a little arrow there, and you would say 0 volts for the 0 level. You could draw a little arrow on the right-hand side like this for the trigger. You could indicate that with a T maybe. It says to indicate the peak-to-peak voltage. So you could do something like this. Say that we wanted it to be 8 volts peak-to-peak. You would write 8 volts from the top to the bottom. Some of the graphs ask you to indicate the period. So you could do something like this. You could say 1 millisecond from there to there. And then down at the bottom, you want to make sure that you indicate the volts per division and the time per division. So you would do something like 2 volts. There's a little box that you have to fill in. And this is the volts per division. Remember, it's not the peak-to-peak voltage. It's not the maximum voltage. It's not anything else. It's the volts per division. So you would write in 2 volts down there, and then something like 100 microseconds. And that's the time per division. Okay? So you draw your signal carefully. You indicate the 0 level, the trigger level, the volts per division, the time per division, and then also the period and the maximum peak-to-peak voltage for your signal. Okay? So that's what you should draw in your lab book. Any questions about that? Okay. All right, so the rest of your lab is going to be very similar. You're going to be creating different shapes of waves, different amplitudes, different frequencies, but the idea is the same. You create the wave, you set all the settings where they need to be, and then you sketch it in your lab book. And you're going to indicate the same things on each sketch. So any questions about that? For homework, please do the oscilloscope crossword in your lab book. And remember to bring safety glasses for next time because we're going to start on this other. All right? Okay. Unless there's any other questions, I will take roll and let you go.